Hi everyone, I am Anoma. I am a PhD student at TIFR and this work is done with Rishi Khatri and Tuhin Roy. Okay, so as we know, dark matter constitutes a major fraction of the matter content in our universe, about which apart from gravitational interactions, we know very little. Now, one of the ways people look for dark matter is through indirect dark matter searches, where they try to find standard model particles that may be created when dark matter decays or annihilates. But those signatures mostly fall into the category of emission signatures of dark matter. Whereas absorption signatures of dark matter is a very less steady territory, and there's a huge parameter space that is waiting to be explored. And this is what I'm going to tell you about today. So the idea is that if you have a background source and dark matter has a weak electromagnetic coupling, then it is possible that it can absorb a photon from the source and imprint an absorption line in the spectrum of the source. So I'm going to tell you about these absorption features for two kinds of sources. One where the source is CMB, which I'll relate to the edges observation, and when the source is a compact source like a quasar, which gives rise to dark forest. Okay, so to do the physics of absorption lines, we can simply consider dark matter to be a composite particle with two states. This is the ground state and the excited state with an energy splitting delta E. Now, dark matter is going to populate both of these states, which we can write using the Boltzmann law, where the excitation temperature characterizes the dark matter population. Now, the different processes that are going to affect this population are of two kinds. So if dark matter has a small electromagnetic coupling, then it will just be a photon absorption or an emission, which will decide the population or the excitation temperature. And if dark matter has self-interaction, then there can be inelastic collisions, where collisions can cause this excitation or de-excitation. Now, when we put this picture into our universe, where we have CMB as the background source and there is dark matter, these two systems now interact via these two state transitions. So if the radiative transitions dominate because of CMB temperature, then the population is going to be decided by the CMB temperature. Whereas if the dark matter inelastic collisions dominate, then the excitation temperature will be decided by the dark matter temperature. Now, this is going to lead to a global absorption feature in the CMB spectrum, which can be seen from this plot. So here there are the three temperatures of the problem: CMB, dark matter, excitation. And what you see is that at some very high redshift, the dark matter and CMB was coupled. They had the same temperature. But as dark matter decoupled from the thermal plasma, it was non-relativistic. So its temperature started falling as 1 plus z square. But at these high redshifts, the dark matter number density is high, such that these inelastic collisions dominate, and dark matter, the excitation temperature is equal to dark matter temperature. So it traces the black line. Then what happens because of that is now we have CMB and we have the dark matter. So dark matter has a lesser temperature compared to CMB and it starts absorbing photons. So on the right-hand side, you see the energy spectrum of CMB, and this is with respect to perfect black body. So if it goes negative, it's going into absorption. So it goes down. And then as the number density of dark matter dilutes, the inelastic collisions are no longer efficient, and it is the CMB that decides the level population. So if medium and the CMB have the same temperature, then the absorption signal vanishes. But this would be the story if we just had CMB and dark matter in our universe. We also have baryons. And the important electromagnetic interactions like Compton scattering, Compton scattering, double Compton scattering, and Bremsstrahlung are very, very important in establishing the black body spectrum of CMB. So because of these interactions, what's going to happen is that this black line, the absorption feature at high redshifts, is going to get erased, and we are only going to be left with this small region where this global signal can survive. But this is very much dependent on the energy splitting of dark matter and the frequency of the CMB photon being absorbed. Okay, so now to put it into perspective, in 2018, EDGES observed a global absorption feature in the CMB in 50 to 100 megahertz band, which cannot be explained by the usual 21 centimeter cosmology. So our dark matter for a viable, or for a wide parameter space can produce these global absorption signals, which is consistent with EDGES observations. But of course, later on, Saras told us that they disproved the EDGES claims. So this is just to say that this global absorption feature is not a prediction for a particular band. It could exist in any part of the electromagnetic spectrum. So you can see that how the global absorption feature changes with the change in the energy splitting. It is also a function of the collisional interactions of dark matter, so that changes the shape. And also if you increase the electromagnetic coupling, then the amplitude of the signal increases. So instead of global absorption feature, absorption of CMB photons by dark matter can also lead to spectral distortions. And there are limits on spectral distortions from COBE. So this is a preliminary result where we have tried to constrain the coupling of dark matter as a function of the energy splitting of dark matter for mu and y distortions. Okay, so now I'm going to talk about what happens if we have a compact source like a quasar. So this is a picture where we have a compact source and there's a dark matter halo, and the line of sight intersects the dark matter halo at a certain impact parameter. And this can be quantified in terms of something called optical depth. So the optical depth is proportional to the coupling of dark matter to photons, the number density of dark matter along the line of sight, and also the random motion along the line of sight, which is going to give a width to this absorption profile. And again, the excitation temperature, which decides the population of dark matter halo, dark matter particles in ground state and excited state. For here, we took two extreme scenarios, one where we considered collisionless dark matter. So we just have photons which are making transition. So it is just the CMB temperature. And the other, if inelastic collisions are strong, then the excitation temperature is equal to the dark matter halo temperature. Now, this is just to show you how the optical depth profile changes for two kinds of dark matter particles. So we find that this is sensitive to dark matter self-interactions. We have stronger absorption for more massive halos, just because the number density of dark matter particles increases. And if it is collisional dark matter, because for high mass halos, the virial temperature is high, so there are less particles in the ground state. So there is an opposite feature. But in principle, we will have multiple dark matter halos along the line of sight, and each of these dark matter halo will absorb a photon from the quasar at its rest frame frequency. But due to expansion of the universe, each of these lines are going to redshift, which is going to give us a forest. So this forest is a collection of absorption lines with a certain amplitude and a certain width. So we just counted these lines for a certain amplitude and a certain width and made 1D PDF, and we found that this amplitude was sensitive to the dark matter self-interactions. Collisional dark matter had stronger absorption compared to collisionless dark matter. It is also sensitive to the number of halos along the line of sight, so the low mass cutoff in the matter power spectrum. Then for the line width, we found that it is again sensitive to the small mass halo cutoff in the power spectrum, in the matter power spectrum, and it is independent of dark matter self-interactions because this is just due to gravity. The width comes because just due to gravity, not due to self-interactions. And now coming to the detectability. So in the full electromagnetic spectrum, we have lots of different spectroscopic surveys from mu-GMRT to XMM, Newton, Athena, going till X-ray. And to detect the dark forest, the current optical and radio wave band experiments can do it because they have the required sensitivity. Further, if our model is the correct explanation for edges, then we expect to find a corresponding forest in the VLA band of 20 to 40 gigahertz. So that can be a confirmation. And till now, I told just about the signatures of dark matter, but the kind of model which can give rise to this dark matter is a composite particle made of two elementary particles having epsilon minus epsilon charge, so overall electromagnetically neutral. But since dark matter has to be stable, the stability comes from the strong interactions of dark matter, and the hyperfine splitting between the ground state and excited state give rise to this absorption signature. Okay, so to conclude, in this work, we propose unique signatures of dark matter that can exist as absorption lines in the spectrum of a background source. They could be a global absorption feature or a spectral distortion in CMB. And it could also be a dark forest in the spectrum of a quasar. And if we are able to detect this dark forest in the part of electromagnetic spectrum where we don't expect any lines from baryons or atoms or molecules that we know, then that could be a smoking gun signature for this dark matter. And we can already look for these signatures in the existing data. Thank you.
Thanks for this nice talk. We have time for questions.
So one type of dark matter that's supposed to couple to electromagnetic radiation is the axion. How much of this would apply there?
So axion is an elementary particle. So we are considering a composite particle. So it is a bound state and it has energy levels, just like you have for example, for an atom. In that sense, it is different. And overall, it doesn't have a charge. So it's neutral.
So is there a concrete model that for this kind of thing? Or is the two-state model just a toy model?
Yeah, so one more thing I can add for axion. Axions have masses which are very small, right? These are electron volts. In our case, we consider dark matter mass to be above 10 MeV to be safe from the bounds from early universe like BBN, etc.
Okay.
And regarding the dark matter model, I did not go into the details of this, but in our paper, we have constructed a full model so this is the dark sector where there are two dark quarks with epsilon minus epsilon charges. So in the UV, when the strong interactions are weak, like at energy scales above the confining scale of the strong interactions, these are weakly coupled, so they exist as elementary particles. But once the phase transition of the strong sector in the strong forces in the dark sector happens, these start forming these bound states. And then this is a heavy light bound state. So
so are they forming an atom? The two quarks?
In a sense, it is an atom, but
so it's a bit like H1 emission or absorption.
Yeah, but that is just because of electromagnetism. The binding energy is just due to the charge of electron and proton. Here it is due to the strong forces. It's like a neutron, you can think in that way.
Okay, thank you.
Okay. So the forest, can you just bring up the plot that shows the forest again? Because I'm looking at it and it reminds me, so it's like a Lyman alpha forest.
So it's more like a 21 centimeter forest. So because the coupling to photon is very weak. So because Lyman alpha forest, I mean, it goes into strong absorption even for like 10 to the -3 of, I mean, if you have neutral hydrogen.
Okay, because I was wondering if there's an equivalent of, like, is there also some small net suppression just from the mean density?
Sorry?
Like, is there also something like the Gunn-Peterson? Like, is there some small overall suppression just from propagation through the cosmic mean density?
Yeah, so then I think we would have to model like the distribution of dark matter around the quasar, which is going to give rise to that trough that you're talking about. So this was more like this plot is more for the dark matter halos along the line of sight.
Right,
not
but
exactly
what about the stuff that's not in halos? Does that just give you some general small suppression everywhere left of wherever the
yeah, so that dark matter number density is going to be very small in the voids. Right? So the reason why we chose dark matter halos was because these are the dense structures and this will give the strong absorption line. But in principle, you will have absorption line even in the voids. That's going to be very weak and difficult to detect. Mainly the strong ones will come from the center of the halo, closer to the.
Okay.
I have a question. So I see that this absorption feature can be there in broad spectrum. So is there any challenge in detectability of these features?
You mean for the
From
CMB?
existing data, what are the challenges to detect this feature? Or you haven't yet detected it?
No, we haven't yet detected, but I think we have to make a power spectrum for these absorption lines and then try to fit it there. We have to take care of interlopers also if there are some other lines from the baryonic sector which can be there. I think, yeah.
Thank you, Anoma, for this talk.
Thanks.